In this note set, we're going to look at extrema and the mean value theorem. We're first going to look at the extreme value theorem. And we're going to look at a motivating example first. So the following plot was published in the article Circadian Variation in Swim Performance. And so let's take a moment and kind of first digest what's happening in this plot. So notice along the x-axis we have time of day. And one thing to notice is we start at 0 and we go up to 2400, and then it resets at 0 and goes up to 2400 again. So one thing that can be a little bit deceptive of this, looking at this plot, is notice if I were to draw a straight vertical line right here at 24 hours, that the plot actually repeats itself. And so my guess is the authors did this just to make it easier to look at time and kind of see how this pattern is going to repeat through time. But looking here, notice just as some examples, this point and this point are exactly the same, this point and this point are the same, and even up here, these 2 points are the same as these 2 points. So really, if we wanted just to consider the unique data points, we could just look at one half of this plot to see this. So the authors looked at the relation between body temperature and swim performance rhythms. Both rhythms are double plotted, and so you can see that here. And the swim performance rhythm consistently lagged behind body temperature rhythm. Pre-swim body temperatures was significantly associated with swim performance. And I've cited this article at the end of this note set if you're interested, but you don't need to read the article. Really what we want to focus on here is just looking at the body temperature over the 24-hour period. And notice that the mean body temperatures are given by the black points. And so the question is, what is the maximum and minimum mean body temperature over a 24-hour period? And so if we look here, looking at the plot, it appears that the maximum body temperature occurs here at about 1900 hours, and the minimum occurs here at approximately, we'll say about 2 a.m. And so further, the question I ask here is, if we were to repeat this study, would we be guaranteed to have a maximum and a minimum over a 24-hour period? And so you might say, well, of course we are. If we're going to measure temperatures over a 24-hour period, we're going to be bound to have some minimums and some maximums within that 24-hour period. Now, it doesn't mean that the minimum and maximums are unique. It could be that the temperatures recorded over a 24-hour period were all the same, in which case the min and the max would be equal to another, but they would exist nonetheless. But what exactly is it that guarantees us to have a maximum and a minimum within an interval of time or some other interval? Are we always guaranteed to have a minimum and maximum? And it ends up that we're not always guaranteed to have a minimum and a maximum when we're looking at a function. And so one of the things that we're going to look at in this chapter is, when are we guaranteed for a function to have a minimum and maximum? What conditions need to be met? And so we have a definition here. And so we're going to let f be a function defined on D, and D is going to contain the number C. Then we say that that function has a global, oops, I didn't even mark that out, I meant to highlight it, a global or absolute maximum if that function evaluated at C, its value is greater than or equal to the function evaluated at all other numbers in the domain. And to have a global or an absolute minimum, it's the same thing, except the function evaluated at C will be less than or equal to the function evaluated at all other values in the domain. And so one important thing to notice here is that we do have the equal sign in the inequality. And so this is what guarantees, when we talked about earlier, and I said, we could have the same temperature over the entire 24-hour period, and that would still be the maximum and the minimum in that case. And so this equality sign here allows for that. It's not saying that the maximum has to be a unique number, it's just saying it has to be greater than or equal to the function evaluated at all other values. And so in a case where the function is always a constant value, you would still have a minimum and a maximum. And so the following result gives conditions under which the global maximum and minimum collectively, or called global or absolute extrema, exist. And so here we have two conditions. If f is continuous, so we need f to be a continuous function, on a closed interval, so we also need a closed interval, then we are guaranteed for that function to have a global maximum and a global minimum. And so if we go back and we think of that example of body temperature, if we were to repeat the study, would we be guaranteed to have a maximum and a minimum? And now, not only can we say yes, but we can say why. And so the answer is yes. We can apply the extreme value theorem. So how can we apply the extreme value theorem here? Well, first notice we have a closed interval. We were interested in the 24-hour time period. So our closed interval would be from 0 hours to 24 hours. Or another way that we could write this is we could go ahead and bump this up to the 25th hour, because if we think about how the interval of time is going to work, we have from 0 to 1 all the way up to really 24 hours, 59 minutes, or we could go, butt up to the 25th hour. And so there are ways that we could define this to be a closed interval. It is time, so it seems a little bit funny there, but it can be done. And then the other one is if we consider body temperature to be a function of time, we could define it so it is continuous. And as long as we have both of these, then again, we could apply that extreme value theorem, and we could say that if we repeat the study, we would be guaranteed to have a minimum and a maximum. So let's look at a couple different examples of finding the global extrema, which is again the maximum minimum of a function. Now, one thing that I would recommend is do make sure go through as you're reading the book chapter as well, because the book chapter is going to give some examples that show why we need both f to be continuous and we need it to exist on a closed interval. All right, so looking at this example, here our function is going to be equal to x minus 1, the quantity squared, multiplied by x plus 1. And here, we're going to restrict x between -2 and 2. So first thing to notice this is a closed interval. We could also write this interval like this. That would mean the same thing. And here we have a plot of the function. And so again, we're interested in that closed interval between -2 and 2. So notice if we were to draw some vertical lines to help us out, this is where that closed interval is, and we are interested in the function between this interval. So first of all, notice here that we cross the line x equals 2 at the point 2, 3, and we cross the vertical line x equals -2 at the point -2, 9. Now, looking at the plot, it might be a little bit hard to see, the 3 and the 9 and to know that that's exact. But remember, we could always evaluate the function to find these points. So, for example, if we evaluated f at 2, we would get 2 minus 1 squared times 2 plus 1, which is equal to 3. And you could do the same thing to get the, that should be a -9 here as well. All right, so if we want to find that global minimum and maximum, notice that if we look on this closed interval, the highest point that the function takes on the y-axis occurs at 3, and the lowest point occurs at -9. So in this case, our global maximum on the closed interval from -2 to 2, that global maximum occurs at f of 2, which is equal to 3, and the global minimum occurs at f of -2, which is equal to -9. Now, with that being said, the global minimum and maximum don't always have to occur at the endpoints of the interval. They could occur between the interval as well. So just for example, suppose instead that our function had looked like this. Suppose it came up just like this one does, but then here in the middle took a really large turn and then came back up. So notice in this case, our global maximum would have occurred here instead. So sometimes that global maximum will occur at the endpoints, sometimes it'll occur between the endpoints, and the same thing for that global minimum. Now, what if instead, we had this inequality? So notice in this case, there's no equal sign. And this is what we call an open interval. And we could write it like this. Now, in this case, we're not going to have a global maximum or a global minimum. And the reason for that is this function never actually touches the point 2, 3, or the point -2, -9. It gets arbitrarily close to that point but doesn't touch them. So in this case, if we were trying to figure out what a global maximum would be, remember that we're getting very, very close to 3, but we never touch 3. So whichever point that we pick arbitrarily close to this point here, there's always another point that's just slightly closer. And again, that's because we're constantly getting closer and closer to 3, but we're not touching it. And so this is why that extreme value theorem requires that we have the closed interval, because otherwise if you have an open interval, you're going to have this issue at the endpoints. And if it ends up that that global maximum or minimum could potentially be at the endpoints, but with an open interval you never actually reach those endpoints, you're never going to have that global maximum or that global minimum. All right, so next we're going to talk about local extrema. So we just talked about a global maximum and a global minimum, but we can also have local maximums and minimums. So let's see what that looks like. So local extrema are going to be points where the graph is higher or lower than all nearby points. And so we'll need to talk about what it means to be nearby. And so here is the formal definition. A function f is defined on an interval D, has a local or relative maximum at a point C if there exists some delta greater than 0 such that the function evaluated at C is greater than or equal to the function evaluated at x for all x that are within delta of C. So this looks really complicated, but really all that it's saying is that if you think of a number line, so let's say we have a number line here, and we're going to evaluate at C. What the delta is saying is it's saying that there's some value delta that we can define. And so this would be C plus delta and C minus delta, so that within this region, x evaluated at C, or probably f evaluated at C, is going to be higher than all the other values in this yellow region. And so this is what it means to be nearby. And we don't define a number for delta because delta could be big or it could be really small. And so let's look at kind of an example here to see what we could mean by that. All right, so I've drawn a function here, and notice that this function has different what we would call peaks and valleys. So these are all peaks. And then everywhere it dips down, we could call a valley. Each of these peaks is a local maximum. And so notice I could define a region for this peak, for example. And if I define a region like this, then notice within this region, the function is the highest at that peak. Whereas all the other points within that region, the function evaluated at those points is slightly lower. So in this case, that yellow space that I've drawn there, that's a potential delta. And again, the reason that we don't assign a number for it is notice that if I were to try to increase delta, maybe like all the way out here, notice there are other peaks within delta that are higher. So by defining by delta, it lets us define nearby. In other words, we just get close to where that peak is, and the function evaluated all those points in that small neighborhood are going to be less than what they are at the peak. Now, each of these peaks we would call a local maximum. Now, for this particular picture, we would say that the global maximum is this one because this is the highest peak. So this one would be the global max. And notice that the global max is also a local maximum. And so one way to find a global maximum is to find all of the local maximums and then find which one is the highest. And then we could do the same thing with the valleys to find the local minimums. And so notice for each of these three valleys that we have, this one is the lowest, so this one is the global valley, or the global minimum. But it's also a local minimum. And so another way to find the global minimum is to find all the local minimums and then find the lowest value, which is the global minimum. All right, so let's look at an example here. Here we're going to find the local and the global extrema of the function below. So here our function is 3x minus 5. And we're interested in the open interval from -2 to 1. So again, the first thing that I'm going to do is I'm going to draw just a dotted vertical line at the -2 and one at the 1. And again, this just helps me look at the plot and the region that I'm interested in. Now, since this is an open interval, if I look at my function on this interval, notice that we're not actually going to reach the point where x is equal to 1. We're just going to butt up against it. And our function is never actually going to reach the point where x is equal to -2. Again, we're just going to get very, very close to it. And so looking at these points here, we have the point 1, -2. And here we have the point -2, -11. But since this is an open interval that we see here, we have the same issue that we discussed before. No matter what point I pick, I can always evaluate the function at a point slightly closer to either 1 or -2 and get a point that is either slightly higher or lower than the one that I evaluated before. So for that reason, in this case, there is no local, or in that case global max, and the same thing can be said about the minimum. And again, this is because we're evaluating this function on an open interval. Now if we were to change it, and let's say we wanted to evaluate it on the closed interval, if we evaluate it on the closed interval, then our global and our local maximum would occur at the point 1, -2, and our global and local minimum would occur at the point -2, -11. All right, let's look at another example. So again, we're going to find the local and global extrema of the function below. Now notice in this case, we do have a closed interval, And the interval that we're interested in is going to be the interval from 0 to 3. So again, to help myself out, I'm going to just kind of draw those dashed vertical lines. So I'm going to go from 0 to 3. All right, so looking at this interval here, I can see that the highest point that the function takes occurs here at the end point when x is equal to 0. And so notice when x is equal to 0, we could evaluate f at 0. And so that's going to be equal to 0 minus 2, which is negative 2 squared, which is equal to 4. So here we have the point 0, 4. And this, well, hold on just a second. Let's see if we have any other local maximums. So here is another local maximum. And so here we have the function evaluated at 3. And so f of 3 is equal to 3 minus 2 squared, which is just equal to 1. So here we have the point 3, 1. So notice that the point 3, 1, this is a local max. And again, it is a local max because we could look at this region right here. The other point is also a local max. Now these are the only two local maximums, and the highest of them occurs at the point 0, 4, so this is also a global max. Now in terms of minimums, there's only one minimum, and the minimum occurs right here. So the minimum is occurring at the point when x is equal to 2. And so again, if we evaluate the function at 2, we'd find this is the point 2, 0. So this point is the local and the global minimum because it's the only one. And again, this works because we have the closed interval. Now notice if instead we had looked at the open interval from 0 to 3, in this case, we would still have that local and global minimum occurring at 2, 0, but there would be no maximum. So it's still possible to have global or, global or even local maximums and minimums when you have an open interval. It's just not guaranteed that you're going to have them. So next we have what is called Vermont's theorem. And so Vermont's theorem says if x has a local extrema at an interior point C, then the derivative of C and the derivative at C exist, then the derivative evaluated at C must be equal to 0. So why is this going to be the case? Well, let's actually go back up to one of our previous pictures where we talked about the peaks and the valleys, so this one right here. So notice that anywhere we have a peak and a valley, if we were to go through here and draw the tangent line, for each of these, the tangent line would just be a flat horizontal line. And that's a line that has a slope of 0. So in other words, the derivative evaluated at each of these points would be equal to 0. All right, so let's go back to our page with Vermont's theorem. So what we're going to do is we're going to apply Vermont's theorem to find a local extrema point. So to do this, we're first going to find the derivative. Let me change my pen color here. Go. All right, so first we're going to find, that still doesn't look right, the derivative. So by the chain rule, we have that the derivative of the function is equal to e to the negative x squared, and that's because the derivative of e to the x is e to the x. But notice my inner function here is negative x squared. So by the chain rule, I have to multiply by the derivative of that function, which will be equal to negative 2x. And so my next question, in order to apply this theorem, is I need to ask myself, when does the derivative equal 0? And so to find this, I could set negative 2x e to the negative x squared equal to 0 and solve. But notice that e to the negative x squared will never equal 0. So the only way for this entire quantity, oh, that's what I'm doing, I got the highlighter here, sorry. The only way that this quantity here is ever going to be equal to 0 is if the negative 2x is equal to 0. So we need negative 2x to be equal to 0, or in other words, when x is equal to 0. So the question we now ask is x equal to 0 a minimum or a max? Because Vermont's theorem doesn't tell us which one. And so one way to check this is we could look at a graph of the function. And so here I have a graph of this function. Another is to test the points around 0, so for example negative 1 and 1, to see are they higher or lower than when we evaluated 0. And then later on in the notes, we're going to see how we can actually use the second derivative to help us. But let's look at this plot and determine. So notice here, when x is equal to 0, we do have a maximum. And so we can see that looking at the plot. And then further, we were just talking about the slope of the tangent line. So notice at this point, the slope of the tangent line is horizontal. So we do see that when x is equal to 0, we are going to have a horizontal tangent line, or we're going to have a derivative that's equal to 0. And in this case, looking at the plot, we can see that that is a maximum. And again, the other way that we could have checked this is we could have evaluated at 2 points that were close to 0. So if, for example, we could evaluate at 1 and at negative 1. And so here, notice that f at 0 is equal to e to the negative 0 squared. Well, we know that any number to the power of 0 is going to be equal to 1. And then if we evaluated at 1, we would get e to the negative 1 squared. And then we could evaluate at negative 1 and have e to the negative 1 squared. In both cases, we get that this is equal to 1 over e and 1 over e. And we can see that here if we were to evaluate at 1 and negative 1, we would expect to get the same value for both of those. But in either case, both of these values are less than 1. So again, that reaffirms that we do have a maximum here, and we wouldn't have had to have the plot to check that. Your book, if you look on page 218 and 219, for example 6, do make sure to pay good attention to that example. It gives good guidelines for finding local extrema candidates, and it's a really good example, so do make sure to check out that example. And then the last thing that you'll see in your book is the mean value theorem, and your text gives an excellent discussion of the mean value theorem and Rolle's theorem, so please read both of those on your own.